Okay, welcome everyone. Thank you for tuning in the day after the eclipse here in North America and South America, I guess. Here in the Western Hemisphere. So our presenter today is Shyama Narendranath from Israel, and I will hand it over to Shama to introduce herself more and to tell us about her work on sodium on the moon. And just a reminder to everybody, so if you're not talking, please make sure your microphone is on mute. And if you have questions, Shama, would you prefer if people wait until the end for questions, or is it okay to ask questions in between?
Yeah, you can please interrupt me. I find that more convenient usually, so that's
Uh-huh.
fine. Yeah.
Okay. So yeah, so if you have questions, feel free to unmute or put the question in the chat. And I will hand it over to Shama.
Yeah, thank you, Parvati. Uh, yeah, I've not been in this group often because the time usually is very late. But yeah, sure, it helps if you have recorded talks online and would be very interested to discuss further with all of you on this. So, we've been mapping sodium on the moon using CLARS, which is a X-ray fluorescence experiment on Chandrayaan-2 orbiter. And since sodium is moderately volatile, I thought that it would be of interest to this crowd. So we have also been measuring sodium in the exosphere of the moon. So Ashish, who's my PhD student, halfway through the talk, I'll hand it over to him because he has been doing all the hard work observing, sleepless nights in the observatory and observing sodium. He's working on that. Um, so I will come from the big picture. Volatiles are of interest. I mean, the abundance of volatiles today are of interest because there are two reasons. One, we know that we all have exploration interests on the moon. So, like the south pole of the moon is a destination, and so from the point of view of exploration, it's very important to know the quantitatively the amount of volatiles on the moon, especially at the poles. But from a lunar science point of view, and for the bigger picture, when we talk about volatiles today, that gives us a point to trace back the evolution of volatiles in the solar system itself. So the conventional understanding of how solar system evolved, where the temperatures in the inner disk were very hot, that there was a depletion of volatiles, or or in other words, condensation sequence says that it was of like high melting point elements like silicon and aluminum that would have condensed in those regions, which is what we see today as rocky planets in the interior, and further away we have more gaseous planets. So this whole picture of how solar system evolved very much depends on what we see today. And one of the important points here is the volatile depletion that we see in the inner solar system. Um, Volatility itself is defined in cosmochemistry as it's based on a temperature at which 50% of an element condenses from a gas phase of the solar nebula composition at 10 raised to minus 4 bar. I put it here because when we say it condensed, there is a very specific definition to it. And so, when we talk about exosolar systems or systems where um, uh, the initial composition itself would be different, the condensation temperature could also be different. So when we say volatile today, it is based on this very specific definition. So that way, sodium, as you can see here, is a moderately volatile element with a temperature in between these values, and potassium as well. Here, the assumption is that the volatile depletion trends during accretion depends on these values of the condensation temperature. There can be deviations, some of which I've tried to list here. For example, if the solar nebula abundances were different, because what we assume in models is from our current understanding of the solar photospheric abundance and the meteoritic values, where measuring highly volatile elements is very difficult. There could be different dust gas ratios, which changes the accretion in the inner disk. It could be homogeneities, non-homogeneities that have happened in the early past. I mean, some all of these factors, and There are more when we get into details, but at least these are major factors which could lead to deviation in the value of the TC. And in that way, when we say currently the Earth Moon system or the inner planets are depleted in volatiles, we mean based on these primary assumptions. So one of the questions to ask is, how did the Earth Moon forming impact affect the thermochemical evolution of the system? There has been a volatile depletion trend in the inner solar system, and the Earth Moon impact, the moon lunar formation impact that had happened would also have contributed to this volatile depletion that we see today. Sodium, condensation temperature is about 950 Kelvin, according to the paper, Lauder's paper. And there's a clear depletion on the moon, as you can see on the right. If you take sodium, for example, relative to Earth is the top curve, where relative to the H-chondrite is the curve down. So you can see that if you assume you have one on Earth, how much it is depleted on the moon. And moon, we know the major mineral on the surface of the moon is plagioclase feldspar. So sodium on the moon occur as solid solutions between albite and anorthite. And because of the alkali depletion on the moon, it's more of anorthite than albite. Now, we say there is an alkali depletion on the moon based on the return sample values and what we find in meteorites. So this fundamental assumption or rather understanding that there's been an alkali depletion on the moon is because of the abundances in the return samples in meteorites and the models that we have of the thermal evolution of the moon. It has been very difficult to remotely observe sodium on the moon. There's been the first time a detection in X-rays using Chandrayaan-1 kicks in this paper in 2014, where there was a clear detection of a line, but it was a small area, so there was no subsequent mapping. And there was in 2021, I find there was a LPSC abstract which talked about sodium lines in gamma rays. This is using the Kaguya GRS. But here it's a whole moon average because it's a very weak signal, as you can see here. If the spectrum is for the whole moon. Now, class, we are able to see this particular line that you see here at 1 keV. We are able to see that further from the orbit, and we've been able to map it using this X-ray fluorescence line of sodium. So X-ray fluorescence happen when there is a solar flare, and that triggers a X-ray fluorescence photon. And when you observe from the orbit, the intensity of the line is, not really proportional, but that is related to the abundance, and the energy of the line gives you the atom. So that way, detection itself is a very straightforward. Whereas converting that to abundance do have some dependencies on the models that we use. Now, there has been an earlier X-ray fluorescence experiment, so one would ask, like, how is that now class is able to map it? So just for a comparison, the main reason why was because in earlier kind of instrumentation that we had, you could only measure the major elements, magnesium, aluminum, silicon, and it was from Smart 1D kicks that these kind of instrumentation was flown. But Smart 1 had a long journey to the moon, and so there was some severe radiation damage that has happened. Kaguya GRS was also, the CCDs were damaged due to radiation by the time it reached orbit. And Chang'e 1 and 2 had a very small area. So basically, class is able to do this only because there's really the effective area of the instrument is quite big. So that way you can say this is the most sensitive of all the X-ray fluorescence experiments that's been flown to the moon. We've also developed algorithm to convert the X-ray spectrum that we see into abundances. This being tested with several experiments on ground. So basically we take the spectra, we find where the lines are, and then you use a model that includes the solar spectrum, use a background, use a scattered component of the solar spectrum, and finally derive the best fit abundances iteratively by changing the parameter values. Very important here is to have a measure of the solar spectrum that's falling on the sun. So there is a X-ray solar monitor on board which looks at the sun simultaneously as class looks at the moon. So this is to give an example of a spectrum during a C-class flare. So C-class is a relatively lower flare than these higher flares. But what you see is that because the continuum from the sun, the scattered part of the X-rays from the sun is very high when you go to very strong flares. It's relatively easier to detect sodium for the middle class flares like this. So here, this is the sodium line that is detected. As you go to very strong flares, it gets, the line to continuum ratio is weaker. So we have selected such spectra where there is a clear detection and mapped it into abundances. So this is update of what is in the paper. So further, the paper had like a year of data, but this is further on adding to it. So what we clearly see is higher abundances towards the poles. Now, one thing is that we do not get a good signal above 85 degree because when you go to really the poles, it's grazing incidence and the signals are really weak. So the measurements that we have is like plus minus 85 degrees. But clearly we see a trend where the abundances are higher towards the poles. And I'll come to further another trend that we see, which led to a model that and where we suggest that there is a volatile component to it. If you plot the abundances that we get with typical values that you find in soils, the trends are similar, and we do even have calibration points for example, Apollo 17 values. They do exactly match what we measure from class. So there's some amount of confidence in the abundances that we have derived using class. But however, a global average is higher than the typical values that is in the samples.
Hey, Shyama, could I ask a question?
Yeah, sure.
Yeah, so I think this might be like a basic X-ray fluorescence question. But so how frequently do the flares happen? Because you guys need a flare to be able to get
that's right. So when we started off, solar activity is like approximately 11-year-old cycle. So when we started off in 2019, the sun was really low. Currently, the sun is almost at the peak of its activity. If you see this year, you have very strong flares all the time. The background level itself is very high. So, like every maybe in a day, you might get 10 to 15 flares. It's that order currently. But when the solar activity is low, it's like a whole month can go without a flare. So that's where if you notice, we have taken data from April 2021. Before that, it's been like there are very few flares. So yeah, that's a constraint. That's also why most of the earlier X-ray fluorescence experiment we never finished mapping it because you have to wait for a solar flare to happen something. Unlike in infrared reflectance spectroscopy, for example, you all the time get a signal. So here we have to wait for this sun to flare.
And so do you know, I mean, so the map you showed on the previous slide is really interesting, but do you have an idea of, I mean, would you eventually be able to map the entire moon? Like, or do you have a sense of how long it would take if you really wanted to get a global map?
Right. So so for the other elements, we have completely covered it. Like there's a whole coverage. In the case of sodium, there might be a coverage, but we've been just really, really very careful in because it's a weak line. We have discarded spectra where there's been any doubt on because of the strength of it or when it converting to abundance. So Netra, if you want to add, please do. So Netra is actually doing the spectral analysis.
Yeah, I just put it in the chart. So because of the higher sensitivity, what essentially happens is that even when the active spots start appearing on the sun, we're able to observe these lines. And currently, with the amount of data that we have accumulated across about 5 years, we can make like almost completely cover global maps of magnesium, aluminum, and silicon. Sodium, we have like this is the most recent map, but these are basically spectra with very good fitting statistics. So
Mhm.
if I mean our next attempt would be to focus on certain geologically interesting regions on the moon and prepare these higher resolution maps like at the grid of about zero point 0.1 degree by zero point 0.1 degree. So that's sort of where we're going towards. But yeah, I would say we have significant coverage even right now.
Okay, awesome. Thanks.
Mm, yeah. So when we look at the trends, there were two things that we seen that there is a tendency of the sodium, the larger data points seem to be at the higher latitudes. And when we actually looked at the changes with local solar time, you see that for the same pixel, there was a change with local solar time. We developed a Monte Carlo model. It's a very simplistic model, but this was sort of to try and see that can we claim that some part of the X-ray signal that we see comes from a surface layer of adsorbate of sodium atoms. So what we did was to basically construct in GIAN4, which is a Monte Carlo simulation toolkit, lunar surface to the depth where X-rays penetrate. So this can be like a few tens of microns, and then vary the sodium in the lunar soil and see how that signal will vary if we just increase sodium weight percentage in the soil. This we compared with magnesium so that there is a reference point to say this is how it should vary. And if you had a varying adsorbate layer on the it's like there's an independent layer of atoms on the surface of the lunar soil. How would this trend be? So this curve would look like this if the signal was coming from an adsorbate layer. And then if there was a varying sodium adsorbate thickness, this is how it would look like. So we fitted with these models the data points and concluded that it should be roughly about a 5 micron layer of sodium adsorbate that's what would give us these higher values of abundances. So it's a kind of crude model, but basically this only would demonstrate that this helped us to say that a part of the signal that we see in X-rays is probably coming from a surface adsorbate layer that's varying spatially as well as with time. And so the inferences we made from these is that the X-ray line flux, as I said, partly comes from the adsorbate layer, and it changes with time. It's higher at the poles. So, for example, here you see with the local solar time how the sodium is varying, and with latitude how this was. And so we also observe a north-south asymmetry in the sodium weight percentage, as per the model and data. A very important part of this was that we should have modeled the scattered solar spectrum very well, because at 1 kV, for example, here is a very high resolution solar spectrum. This is for a quiet sun, but just to give an example, there's a forest of lines here. So when you calculate a scattered spectrum that forms part of this continuum here, we need to take into account the strength of these lines. And I mean, basically, all of these transitions should be taken into account when we calculate a scattered spectrum. So that's what we actually did, because X-ray solar monitor goes down to 1 kV. So it's just about there. So we fit this using standard spectral models and used what we get from the model at 1 kV. So that's what we have used here. And down here, you can see the deconvolved components where these lines are X-ray fluorescence lines. And down there is a scattered continuum that we calculate from an actual measurement of the solar spectrum. But I just wanted to point out this because the uncertainty that can come here is if you don't have a good measure of the solar spectrum. So XSM is just about there. It just stops at 1 kV. So in future, what you would want to improve is to have solar spectrometers which can go down to, say, like this, up to 0.5 kV, where you really know the spectrum down to lower energies. But unfortunately, like, it's very difficult to look at the sun during a flare at these energies, because there's like huge number of photons, and currently there's no such spectrometers. And uncertainties in the model itself could be in the absolute abundance, though we are pretty sure of the trends, spatially as well as temporally. Like, the next thing is to say how much weight percentage can you say is coming from the mineral, and how much is from the adsorbate layer, like in terms of actually quantifying it. So that's a challenge to do, because either you have to assume that the what is locked in the soil is coming, is typical values of from the samples, and then look at the other component. But then, because the samples are from a very limited region, we didn't go about doing that, because that would really put a limit to other possibilities. So currently that's not done, but so that's something that we're thinking of, like how to proceed in that manner. There is a time variation in the volatile component, but what is that suggestive of in terms of the source process is something that we still need to look at. There is a north-south asymmetry seen. Currently not sure why that would be. But so the idea next, what we thought was to use sodium as a tracer of the surface exosphere interactions, because there is enough literature to say that we've observed sodium in the exosphere, and there are many papers from the Rosemary Killen group looked at trends in the exosphere of sodium. So naturally, using something that you can see on the surface as well as the exosphere would be a good starting point to constrain the source processes and the trends that we see. The further work that we've been doing is to look at seasonal changes at the poles. For example, this is still needs to be updated, but you can see that there is a tendency that maybe the north-south asymmetry is changing here. When we look at in 6 months chunks, when you look at the data, the trend seems to become other way. And basically to build a theoretical framework to understand the source processes. We've been also been looking at whether changes happen in the geotail. There are some suggestions, but not really confident to say that yet. During meteor showers. So these are some of the things we need to look at. And the surface exosphere connection wise, we've been looking at observing the exosphere with a ground telescope. So this is the first measurement we had with the Vainu Babu telescope, which is in the south part of India. And Ashish, who works with me for his PhD, he is doing this. So I'll hand it over to Ashish to explain the observations from the Vainu Babu telescope, and then maybe we can go to the last part of it. Ashish, please. Hello. Hello.
Yes, ma'am. Can you move to the next slide?
Yeah.
So to start off with, we all know that sodium is a efficient resonance scatter. When the solar light is falling onto the exosphere, the sodium scatters much efficiently, so that sodium is much more observable from far. So based on this, we initial observations had happened in 1988 by Porter and Morgan, and they had observed the sodium D2 and D1 lines, which is shown on the right side figure. And the particle densities and also the column densities have been already estimated, and that falls around like 50 to 100 atoms per centimeter cube. And also the gas population is around like 10 power 5 to 10 power 6 atoms per centimeter cube, which is the column densities. So this has been already measured. So we are attempting to do the preliminary detections and also do further analysis on what can be. So can you move to the next slide? To start off with, uh, the Binary Observatory is actually established in 1986, and which is having a 2.34-meter diameter primary mirror, and that image is shown on the left side figure. This is the telescope, which is on an equatorial mode, and which has a high resolution fiber spread Hessian spectrograph on it. So the spectrographs, the figure of the spectrograph is shown on the right hand side, and as I mentioned, it's a fiber fed Hessian spectrograph. The fiber, the light reflected from the primary mirror actually reaches the prime focus of the telescope, from where that light is taken to the Hessian instruments through an optical fiber. As you can see on the right hand side figure, there is an optical fiber red color cable coming towards the instrument, which enters through a slit arrangement, which is around like 60 micron in size, and also the fiber the size of the fiber is also 100 micron, which spans around like 2.5 2.7 arc seconds in the sky, which is when you convert it to a mean lunar distance, that fiber is around like 5.4 kilometers across, and with the use of this additional slit of 60 micron, we were able to achieve around the resolution of around 72,000. So the advantage of using VBT is that in a single exposure we can probe from 4,000 angstrom to 1 micron, which is having the possibility of if possible, detection of other elements also other than sodium, where we can expect calcium, iron, or the previous literature actually talks about that, where we have a possibility of detecting such elements. And so VBT actually brings in such an advantage. So can you move to the next slide? So our observation scenario actually okay. Uh, we uh, we had faced two challenges. One is definitely the brightness of the moon, because the VBT telescope is actually a stellar telescope, and which is designed for much lower magnitudes of observations. But moon being around like -11 magnitude at full moon, it is very hard to point a telescope towards that. So to limit that, we actually used the 60 micron slit, which we used actually helped in limiting the light. And also we used very short exposure times, like 2 minutes to maximum of 20 minutes was used. And the second challenge which we faced was using the guided telescope, which is like since VBT is a stellar spectrograph or a telescope, it had an auto guider which is actually designed to guide for point sources or stellar like objects. So being moon the extended object, we were not able to use the auto guider. So that is, to override that part, we actually installed an additional camera called as IDS camera on the guided telescope, which is an 8-inch refractor telescope, and we opted a manual guiding mode. We actually spotted different features on the moon, like craters or bright features. And based on that, we guided the telescope. So the figure shown on the right hand side is actually the image taken by us using the IDS camera, and we to measure how far we are moving away, or to systematically move the moon sampled exosphere. What we did is we divided the entire region into the x-axis into 16 segments, and on the y-axis into 10 segments. So when we measure the exact field of view, the field of view of IDS camera is coming around 5 arc minute in the x direction and 3 arc minute in the y direction. So each pixel or each segment which we have divided into is around like 18.75 arc seconds, which is around like 40 kilometers at lunar distance. What we did for observation is that uh, uh, as I mentioned, it's a fiber thread spectrograph. We positioned this fiber at this blue point, and then we shifted the moon towards the east direction. Sorry, towards the west direction. The limb which you are seeing of the moon is actually the eastern limb, and when the moon is shifted towards the west direction, you sample higher altitudes of the in the atmosphere. Can you move? Okay. Okay. Yeah. Uh, Coming to the analysis part, the spectral reduction was carried out using the Eshel spectrum. I mean, the IRAF packages, like IMRED, CCD Pro, Eshel, etc. And we actually uh, uh, okay. In the initial step is actually about extracting the spectra from the raw data, and we performed this using various tasks in Eshel package. And what we did is the entire raw data is actually segmented into 50 layers, uh, which is having uh, which actually the entire wavelength range from 4,000 angstrom to 8,000 angstrom is actually split into 50 layers, and the 28th layer is actually having the sodium emission lines. So we extracted out the that particular aperture. We call it as an aperture or an order, and that was done using the IRF packages. So in so after extracting out the spectrum, we actually did the continuum normalization to remove out the continuum of the spectrum, and also we did telluric correction, which is in standard known as the uh, B star correction. We actually observed a B7 type star, uh, which uh, which is more or less having a featureless spectrum, and whatever absorption lines which you see in such an observation will be coming from our atmosphere. So based on that, we did the telluric correction where the telluric lines were removed from the spectrum, and also uh, uh, that is where the spectral reduction uh, I mean, concludes. After that, what we did is to extract out the exospheric spectrum from the actual the extract exospheric spectrum from the limb spectrum. What we did is we have to remove the scatter component, which is scattered light coming from the surface of the moon, and that part was done using by sampling the disk of the moon multiple times and taking a median disk of the spectrum. So what we did is uh, then we what we did is we cross correlated the disk spectra with the exospheric spectra, so that we don't have any subpixel variations also. So once the both the spectrums are matched in pixel scales, space, we divide out the median disk from the corrected exosphere spectrum from the limb spectrum. So the spectrum which is shown on the left hand side uh, is actually showing each of and every step. The first is the on the left the on the figure on the left hand side, the first panel shows the observed spectra, which is telluric, which is continuum normalized, and which you can see that there are a lot of narrow lines which is present, which is actually coming from our atmosphere. And after telluric correction of the observed spectrum, we get the spectrum in panel B, where panel B, where the more or less the telluric lines are all removed, and the panel C in the left hand figure is actually the median spectra which we made of the disk, and panel D gives the division of panel B and panel C, which is observed spectra, which is corrected for telluric and DIB corrections, and then divided by the median disk spectra, which gives the detection of sodium D2 and D1 lines, which is shown on the bottom panel. So the same thing which is shown on the right hand side, but I have shown two spectrums. One is observed at the first quarter of the moon, and the second one is during the full moon of the full moon. So you can see that in both cases we have detections. Can you move to the next slide? Yeah. So from the initial intensity measurements from of whatever detections we have, the line ratios, we see that the intensity at the full moon is drastically lesser, like is 5 to 6 times lesser than the intensity at the during first quarter. This is from when we look at previous literature, which is this is actually an expected phenomenon, which is caused because the moon is actually inside the magnetic sphere of the moon of the Earth, where the energetic particles are not reaching to the surface, and as previous literature indicate, the solar wind sputtering and photon desorption are the major, if they are the major processes. It is expected that uh, if the less particles reach the surface, less desorption happens, and we detect very less amount of sodium in the exosphere during a full moon time. So coming to the next conclusion or next result, it is the line ratios actually our measurements fall between 1.2 to 1.8, which is actually the expected value that which is previously quoted in previous literature. So to the next slide. So as future work. One difficulty which I have faced is during the full moon time, because since the moon is so bright during that time, the scatter component is dominant, and so removing the scatter is a huge challenge during a full moon time. But that case is not happening during the quarter phases. So this is one thing which we are planning to do in the next step. That's it, I think, from my end. We can have a questions.
Hey, thanks, Ashish. Thanks, Shyama. That was yeah. No, this is super interesting. So, what questions do people have? I can start us off. So Ashish, in your observations, are you mostly looking at variations with altitude near the equator? Can you look at
Yeah.
different latitudes as well?
Yes, we can do that because as you can see in that figure of the IDS camera, I have divided the y-axis also into 10 different segments. But we can't go as high as we go in the equatorial region, but we can move through the various latitudes, and we can also probe the polar regions.
Mm-hmm. And have both of you or anyone else on the team? Sorry. What were you saying?
We actually did the whatever you have asked, different latitudes. So we have already carried out that observation in the last week, or the previous observation which we had. So we are still reducing the data so that we'll be able to see the detections.
Yeah. So, Parvati, what we hope to do is to start connecting what you see. I do not know whether you can really make will you see a direct connection, but that's what we want to see. And probably that could constrain at least the time scale of the processes that's happening. That's the basic idea.
Yeah, no, that's super interesting. Yeah, you anticipated my question. Yeah, no, that's really interesting. What I guess let's say I wrote down a couple of things. Yes, so could you say a little bit more about the north-south asymmetry, as in how do so I guess how confident are you that that it's real and not just based on where you have your observations, and also any ideas on why that might be the case?
Yeah, so like actually the reviewer asked when we submitted the paper that is that going to flip, or do you expect then, based on how the alignment is, even though it changes very little, but in 6 months would you expect a change? And that's why in the first place I actually tried plotting in 6 months chunks, and so it did suggest a flip from north south to south north. But we didn't include that in the paper. I probably need to look at that again. So only reason is probably the angle. Just trying to see. Yeah, I think just in 6 months how the angle changes. Though yeah, you don't talk about seasons there, but the slight variation probably.
So you mean the angle of incidence of the sunlight at the poles?
Yeah. That's probably one. So I mean, the main motivation I think is that because you don't see water in the exosphere, this is probably a place where you can see whether test models where from the surface and exosphere, and see if you can extend that to other species. So that's a possibility. And since in Mercury as well, you see sodium in the exosphere, and there is a possibility that mixes which is on Bepi Colombo would see this, because earlier Messenger did not have I mean, it again had proportional counters which wouldn't have seen sodium, but mixes that's going on Bepi Colombo probably can. If so, again, you have another surface boundary exosphere where you can see it in the exosphere as well as the surface. So therefore, maybe it's good to take sodium as a tracer. And this is also something that you see in exoplanets. So there are several exoplanets where in the atmosphere, at least, sodium is measured. Yeah, surface is not possible, but there's some scope for extending this to other systems.
Yeah, the seasonal thing is really interesting. So you think you were seeing more sodium or on the surface during the southern hemisphere winter? Is that right? Okay. Yeah, interesting. And the other question I had, and then I will let other people ask questions. So the slide you had where you were talking about the Giant 4 simulations, like so what is the spatial scale? I mean, so how deep do the X-rays sense?
10 to 20 micron. So it's a very, very top layer.
It's micron scale. Okay. And so I was thinking of so I know Menelaus Sarantos and I think Francois Leblanc has done this for Mercury, but so there's been some work into how sodium might diffuse into the subsurface. So could the I mean, did you try moving the sodium layer below the surface?
So so Menelaus is a co-author in the paper, but he did test some of these things with his models. And, but we did not, when we have to do further work on it, probably to get into that level of modeling.
Okay. Yeah. No, this is super interesting. And is KICS always pointed towards the surface, or are there times when other instruments are pointing and so it's not?
It's always not there. It's always not there. I mean, unless you ask for it. But yeah, I don't know if you can really see exospheric sodium. Yeah, but that's a good point. Yeah, try that, because recent paper from Kaguya that I put it in the group, they seem to be seeing water from a sort of plume that they call when in limb mode.
Yeah, no, I was actually just thinking of whether is it always collecting observations, or but yeah.
But as I said, maybe if you do a cross section of the exosphere, I don't know whether you'll see something from the exosphere itself.
Yeah, interesting. Okay, what other questions do we have for Shyama and Ashish?
Hi. So I have two questions, one for each of the speaker. So for Ashish, when you say that the intensity of the sodium is less intense during the full moon, are you looking at specific local times in the exosphere, like I don't know, dawn and dusk, I guess, on the full moon compared to the same region in the first quarter?
Your question is about why is the intensity less during the full moon, right?
Yeah, like
that's what I
where
got.
you look, where you're looking around the moon. So you're looking like on the
Okay.
like the dawn, dusk.
I couldn't get your question
And
completely.
it's just geometrical. I think it's just a geometrical effect.
It is actually what previous literature talks about is the major source processes of releasing sodium from the surface is solar sputtering, ion sputtering, and photon desorption. And once the full moon, during the full moon time, the moon is actually geometrically, it is inside the Earth's magnetosphere. Sphere. Right, so the whatever particles or energetic particles coming from the sun is actually deviated away by the magnetic field, which is not reaching the surface of the moon to cause the release processes. So it is expected that the intensity of sodium lines, which is reaching the exosphere, will be less when the moon is inside the magnetosphere. And when it is in the other quarters, first quarter and third quarter, it is actually outside the magnetosphere, and which is having direct the solar particles reaches the surface directly, so that the release process happens. So we expect a higher intensity at that particular time during the quarter.
Okay.
So
That's what I
so
think
so it,
is the answer.
yeah, so it sounds like it's more of a source mechanism difference than a local time difference. So when you're at the full moon, I guess you're looking at dusk or dawn. I guess that's one of the things Cesare was
Yeah,
asking.
both, right? Depending when you're looking,
Yeah.
right or
Yeah.
left, I guess.
Yeah, we can probe both the equatorial regions.
And okay, so a question for Shyama about the so you talk about what was that the difference between the thickness, I guess. So basically, you can constrain the thickness from your signal, right? You can see what thickness matches your signal. And about the local time dependence, is there a way you can sort out the local time dependence? Maybe, I don't know, looking the same region with different local times. I guess you need to have the same type of flares. A few obviously.
Yeah, so the dependence on the flare strength is removed because you actually model
Okay.
using what is incident. But we do not have many pixels where exact same pixel is measured at different local times.
Okay.
So as you said, further on when we have a full coverage, that's what we have to show that with. Because this is a sort of average because you don't get coverage in the same pixels again and again. You also need the solar flare. But that's right. Further on, we need to pick up pixels where exact same pixel is observed at different local times. Yes.
Thanks.
You really show that. Yeah. But yeah, so that's something like in the sense because local time would mean temperature as a major source process. I think.
Yeah, but it also, I guess, the abundance of sodium absorbed, right? I would expect is greater during the morning, I guess, and late afternoon.
Yeah.
But yeah, very cool study.
And I see Atre has his hand up.
Yeah. Hello, everyone. I'm sorry, I joined late. I just wanted to follow up on the comment which Cesare was giving. So there are about the local variation and the global, which is around about a month of the lunar cycle. So LRO papers, they suggested that when they compared potassium versus sodium, they could see variation in sodium. And that's where in the 2015 and 2016 papers, they talked about the reservoir. So the model which Ashish was mentioning, where the inside the tail, the particles which the lunar surface is experiencing is different from what it is experiencing from the solar wind outside the geotail. So, and somehow there is a process which is again mentioned in the in the LRO paper, that they say that there is a reservoir, whereas it doesn't work for potassium in the same way when they compare potassium versus sodium in the exosphere. So whereas they see an enhancement in LRO in the exosphere, that's one. And second, follow-up observations by Rosemary Killen and her groups. There was a paper in 2019 by Donna Kripatachi. So they followed up with the ground-based observations to study this, but they don't find um, local variation, but they do see global variation around the moon in their papers, in the JGR paper. So again, this all supports the reservoir process, but the process of how the reservoir is and what is the mechanisms between the surface and the what you see in the exosphere from other observations is something which is yet to be explored, because there are not easy way, as Shyama was mentioning, like to observe sodium on the surface so that you can use that as an input to the model. And this is one which was done in this 2022 paper, where they tried to do like a two-component model. One is in the surface, and one how much the input is changing that. That's what I just wanted to bring that up.
Yeah, thanks, Satri. I guess we have time for one final question, if anyone has one. Okay, I'll ask the final question. So Shyama, so you mentioned some of the previous surface-based measurements. Did any of them operate long enough to look at local time variations of the same spot, or the
You
sort
mean
of point measurements?
You mean the X-ray measurements? Other than class?
Yeah. Uh-huh.
No, so there was only kicks which detected, which Atre did that work. Before that, there's not been any detections.
Okay.
Of
Yeah, no,
sodium.
I thought I might have misheard this, but I thought I heard you mention that maybe during Apollo or some of the other.
Oh no, that's all in the return samples, right?
Okay.
Remotely, there was only one previous measurement, but then yeah, Chandrayaan 1 was only for 9 months, so we didn't have a lot of data on this.
Okay, and how's Chandrayaan 2 doing? I mean, is it in a stable orbit? Like,
so it's currently in a 50 to 150 kilometer orbit. It's come down. So in fact, we have very good photographs of the slim lander. I mean, I hope they release that. That's been pushing for that. But you can see the slim lander really well because it has a 16 centimeter, 16 centimeter pixel observation. Because we've come down now. So that's good for OHRC. For class, because it's been 5 years, it's slowly degrading. But otherwise, it can go on for a few more years, definitely. I mean,
Okay,
fuel-wise,
yeah.
there's no problem. So just going on.
Great. Okay, so one final call for any final questions or comments.
Thanks for joining.
Yeah, if not, we're at the top of the hour. So yeah, thank you for joining. And I know there were people who were interested who couldn't make it today. So once the recording is up on the website, I'll send an email to the list as well. But yeah, thanks everyone for joining, and
Thank you.
Thanks Shyama and Ashish.
Thanks,
and,
thank you, Parvati.
Yeah,
Bye-bye.
hoping for more observations.
Yeah, we'll come back later. Yeah. Bye. Thank you.
Bye.
Yeah, bye, Atre.